I'm with the Sales and Marketing Support Group here at EasyPower, and today we're going to be talking about using EasyPower to coordinate systems with large motor control center loads, and we've got a lot of stuff to cover, so I'm going to jump right into it. First, we're going to start with two poll questions. I appreciate the feedback because it helps direct some of this discussion. So the first question is, how frequently do your projects require coordination? It's easy to jump to the assumption that virtually everything does, but I would appreciate some feedback, and like I say, it's going to help direct where we could go with this material. Appreciate people participating. Thank you. And here's what it looks like. And then the second question is, how often do you utilize lumped loads in modeling motor control center schedules? This is a feature that sometimes we slide by as far as discussing it in some of the training sessions, but most of what I have to talk about following this pertains to how you utilize some of the features in the motor control center icons. So I appreciate, again, the feedback here. Here's what people had to say. All right, let's jump into the presentation. So what we're going to be doing today is following up on a discussion that we had last Thursday. We had an excellent presentation from a chief engineer at Eaton talking about the different technologies available for arc flash energy mitigation. And one of the questions that came up was how is a user able to verify the accuracy of the way the models are presented in EasyPower for each of these devices. So I mentioned that we'd start off with that example today, so let's kind of go to the slide that Jim had. Basically, among the discussions that he presented, he talked about maintenance mode, instantaneous trips, and most of these are microcontroller features that are built into the breakers, software trips, zone interlock tripping, quench device enabled, and light sensor tripping. At least three of these are basically time related and cannot be simulated in software at the macro system level. So it's a valid question. How does one implement this in EasyPower? So let's kind of jump out of here and into the tools and see if we can't do some of this stuff. All right, so here's an example of a multi-level system where we have some low voltage power circuit breakers, and then we also have the ability in this particular leg of having arc flash light sensor tripping that could either be applied to a medium voltage trip unit, say a high voltage breaker up even in the primary system, or just anywhere upstream of this bus. So we kind of have two issues going on. One, we want to see the characteristics of this breaker for whatever its design purpose, because it's going to be involved in the coordination with downstream loads. And secondarily, we're going to want to show if in fact there is an arc flash at this bus, how this particular sensor, which is not necessarily sensing current, will respond. So if we go in and look at the characteristics of the breaker itself, this is handled exactly as we would any other breaker by setting up the manufacturer, breaker type, trip unit, the making sure it's in the library, and then the phase trip characteristics with the dial settings, again, which has nothing to do with the arc flash sensor. Because the arc flash sensor responds primarily to time, when we go into the bus itself that we're going to be protecting, each bus has a data dialog box like this, and the arc flash hazard tab allows us to either go with the global settings, which are controlled by short circuit options, or customize the performance of this particular bus during the arc flash calculations to be specific. So in this case, we're showing that user-defined times will be used to calculate the arc flash for this bus, and we're showing that we want the indication to be arc sensing, and again, because our chart says for light sensor tripping, it'll be roughly a 52 millisecond. Now again, these specs are manufacturer specs and they will vary based upon your specific installation, but this is a number that won't come off of a data sheet in our device library. This is a number that will come off of your system in terms of typical tripping for your setup. So that's the time we use here. Now, if I want to show what the tripping time in addition to the TCCs for any upstream devices, I would select use both. So let's see how we're going to use that or how that results. Likewise, on this leg, we have an upstream breaker that has characteristics, but now for the main bus that's being protected, we go to the arc flash hazard tab, and here, this is an active response that actually shorts out the bus at the base of whichever breaker it's applied to, and its response or its ability to trip or quench the arc is approximately 5 milliseconds. So again, that's where we're going to put in our 5 millisecond trip here. And for now, let's go ahead and look at user-defined and the TCC times just to see where things shake out on the analysis. Now that I've got this set up, I'm going to go to Shortcircuit Focus. Let's just fault each one of these buses at a time. And we're showing incident energy at relatively high level. If we look at our range for arc flash, we see that on the light sensor bus, which is the one that we've shorted, when BL1 is the device that's been tripped, the response time or the trip time by virtue of the data sheet is 300 milliseconds, and that's what's producing the arc flash indication, worst case. If, on the other hand, the bus was tripped by the light sensor trip, again, the trip time is 52 milliseconds, and in which case our incident energy would be 1.7 milliseconds. So the moral of the story is I see that the system has the time element is calculated the energy correctly if we have a fault for BL1, and it will still be in play if we have a hard fault, not necessarily arcing related. Likewise, if we go to the quench and we have a fault on that bus, BL2, if it's the trip unit, it'll trip in 300 milliseconds. If the quench unit is the active device or the tripping device, the energy will trip in 5 milliseconds. So when I go back to my my database edit, now that I know that these circuits are in the calculation path, and I will want to use them as we coordinate downstream loads for my arc flash calculations, I think I want to stick with my user-defined time and show the effects of having the tripping device that we've paid a lot of money for. So user-defined times. Now when we go back and trip these buses, we'll see that the results for our study now will indicate the results when that light trip sensor is the one that's in effect, and consequently it will get much more acceptable. Now, how you label that, how you put that on a label is up to you, and we'll leave that discussion for another day. All right, then the third element, let's see. The other element that I want to show is maintenance mode, and this is a feature that's actually in several manufacturers, and has been several manufacturers' feature set for low voltage power circuit breakers, and where it is set up or where it's in the data sheet is once we've described the manufacturer and the trip unit, we verify that it's in the, I say that, these numbers will usually start off with 0 when I put together a part number, and by clicking the calculate, the fact that it changes the number here tells me I found this part number in the database, and the manufacturer guarantees it to work to an interrupt rating of 100,000 amps, and the testing standard is ANSI symmetrical current. Again, when we go to the phase trip, we have a setup now for maintenance, and we can adjust the pickup here to be very fast, and these times will be from the data sheet. In fact, this will only present to us what the data sheet has. So if we start off with the maintenance not engaged, we go to Shortcircuit Focus, fault the buses. We see how we have an incident energy that's relatively high, and BL1 is the active device, and it's tripping as we have our setup. If we want to see and verify what the setting will be turning the maintenance mode on, we right-click, turn maintenance mode on, and now what we'll see is a calculation. Even though BL1 is a tripping device, it's going to have a trip time and arc time of 30 milliseconds, and this is per the data sheet. And so the answer to the question is, how do you know that the software tool matches the data sheet? And the answer is, you can use this indication right here. That's exactly, I guess, one of the reasons I get kind of charged up about the tools, is you can see what's going on in the system. Okay, so where'd that leave us on my presentation? Now, I guess now we jump into the question about MCCs. So I get all carried away and off track. So the question becomes now, how do we coordinate a large load in an MCC? And EasyPower has some very nice features that allow us to do this, and it comes down to understanding what's involved in the MCC icon. If we open up, so here we have a system that has several levels of protection, and we want to coordinate so that if we have a remote fault, it doesn't bring down the whole plant. And in some cases, we may have very large loads in an MCC, and the question is, how do we coordinate with that load with the other devices? I'm going to open up the MCC description, and we'll see that we have the ability to set up many different types of loads within an MCC. And these include a basic motor, a basic load, a VFD, sub-MCCs and sub-panels, motors with TCCs, loads, VFDs, and then lumped motors, less than 50 horsepower group and greater than 50 horsepower group. So what I've done here is set up a motor with a TCC, and the general rule of thumb is you want to coordinate the largest load in the group in the MCC, and as long as you're coordinating with that, then the rest of the system is going to be will behave somewhat in line. So the significance here is that once I've made that designation, I go to the motor specifications, I set up the size of the motor. We may not have the full load current, so we'll calculate that and go to the protective device. Now, this information is filled in, but if you go a little bit further, you'll see once I designate the TCC, it gives me the data button here on the protective device and starter. As I activate that, now it treats this information just like it would a standalone breaker, and from this point on, now this breaker will have the ability, once we get into the device, of plotting the TCC and including a motor overload protective device. So now anytime we plot a TCC that involves this MCC, this particular curve will show up. Now, just because I'm here, I also wanted to talk about lumped motors. So in some regards, If you look at the IEEE instructions on how to regard motor contribution, they suggest that anything less than 50 horsepower is relatively minor contribution as far as fault loads, but if you have a large number of them, there could be some summation that would be worth considering. So the tool allows us to do that both for greater than 50 horsepower and less than 50 horsepower, and the difference there that will come into play is the X over R ratio. So once we add the total horsepower in the group, then the tool will calculate for us the X over R ratio, and here it doesn't make any sense to designate a particular breaker because it's not going to be pertain to any particular load, as well as the conductor that would be part of that load. All right. I'm going to before I go ahead and plot the curve, I'm going to show one more thing here, and that is what if we have a subload, a sub panel, or a sub MCC. So I've actually thrown one in here. Let's turn it on, and here we've got a fairly substantial load to add a sub panel to the MCC. We just select sub panel. It's going to ask us for which cable it's connected to, and then it'll look at that cable and suggest that there's a sub panel out there or a sub load. And once we're there, again, all the information now for the load is going to be grayed out because that's going to be coming from downstream. And as we go to the protective device, again, it shows us a data box or a data block, and we use this to describe the breaker within the MCC now that will protect that downstream load. And again, it can utilize a TCC if need be. All right, so I'm going to take this out. I'm going to take out my sub panel, and we're going to show how the coordination works. Now that I've got a load with a TCC, we're going to want to coordinate, let's say, with this much of the circuit, going to short circuit, coordination. I'm going to plot those TCCs. Right, and again, now what EasyPower will calculate is the incident energy for the bus, the MCC bus itself. It won't calculate any downstream loads. So coordination is still important because I don't want my downstream load to be tripping some upstream breaker. So I'm showing the MCC breaker that's protecting the motor, and so we see here the motor, the MCP breaker, and the motor overload that's been chosen and adjusted to, as much as possible, protect against thermal overload. But we also see now BL4, which is the next upstream bus, and then BL1, which is the further upstream main breaker, and they are miscoordinated. So at that point, I would probably be inclined to make some adjustments, and at that point, it looks like we're in pretty good shape. So if we were to fault this bus, the MCC, again, the main bus on the MCC, the current would be some 17,000 amps. It wouldn't be going through the motor breaker, so I'm going to take that out. And we'd expect this particular breaker to trip first. I'm going to right-click, show my arcing current. And again, the question that can be answered here is, okay, where does the time frame come from? And it comes from exactly where this little trap or triangle crosses the upper boundary. And if you look down here at the bottom of the screen, you'll see the points on my cursor setting. And so we'd expect to see right at 50 milliseconds an arcing fault would clear this breaker. And so that's what would be utilized to calculate my incident energy. Likewise, if I had a fault on this breaker, on this bus, I'd expect this breaker to trip. And again, its time, clearance time would be at the upper edge, and that's where we'd see the almost a half a second. Okay, so at that point, this can be handled just like any other TCC curve. We can create our separation by clicking one curve, holding down Shift, selecting the other, create a difference calculator, and then based upon that being located at our arcing current, we know that we have now about 360 millisecond separation between the time one breaker is clear the arc if it's involved, and the other one starts to sense the fault. Okay, so this brought up so the same thing would be true if I were involved utilizing a downstream TCC. We could coordinate against it. The thing that's missing here, as I indicated and I took out, is my motor control protection, and so we fault the bus. Look at our incident energy. Again, this is the incident energy for the main bus in this MCC. It really doesn't tell us anything about what's downstream to the motor itself. So if I fault all the buses here, we see that the only thing we can label at this point is the main bus on the MCC. We're really not going to be able to label any downstream loads. This may be a problem. So the question came up, what if I had a bunch of loads downstream, and in particular they had, I could label the bucket that they're on as far as the MCC, but because these loads have within them, I need to go to my database edit. If this were my MCC bus and the downstream loads included large loads and lumped loads, how would I model it if I wanted to label disconnects that were downstream of the MCC? Well, the question is handled thusly. First of all, my motor has been labeled, set up, so that we have a large individual load, 150 horsepower. We've calculated X over R, and we can plot the TCC if we need to. A group motor, and again we're doing this because this is the way that we were modeled in the MCC, a group motor can be indicated even on a single load, and now we show a total of 100 horsepower for this load, and we'll calculate a different X over R for the size of the motor because it's going to be less than 50 horsepower. So the question is, how do we produce labels then for these particular disconnects, even if we're not worried about labeling downstream load? The question came up as we were talking with one of our users, tool users, in the, let me see if I can find it, in the field who had worked on a project, and he had built a one line that was pushing the upper limit of his 100 bus license, and he said, is there some way to reduce the bus count here so that I'm not kind of bumping up against it? And he had several MCCs that were loaded with anywhere from 5 to 8 motors each. So the recommendation was, as we kind of go back to our example, the recommendation is to build a standalone system, and the way I want to do this is deactivate this, come back to short circuit, fault this bus, and what I want to do is generate a short circuit report. So we're going to generate a medium volt momentary current short circuit report for high voltage and low voltage, and as we do that, we'll generate a low voltage momentary report that looks like this, and this is for the MCC bus that we're on, MCC2. So we're going to export this to Excel and hold this for a second. And what this is telling us is that this is a 480 volt bus. It's got maximum available current symmetrical amps of 18,523. The X over R ratio is 3.48. And these are the duty amps that a MCC in these particular ranges or a low voltage power circuit breaker needs to meet. So what I'm going to do is come back to this circuit. Let's go ahead and activate this, my database edit. And I want to take a copy of this equivalent, Control C. I'm going to start a new file. I'm going to put this circuit on it. Now what I want to do is to be able to the purpose is to generate labels for these downstream loads while I'm still using the MCC icons in EasyPower, because I want to make sure my client has labels on these disconnects. Even though I suspect they're not going to be large energy, it's still useful to have a label there. So I'm going to put a utility icon on my one line at this point and open up the characteristics for this utility, select my choices to be the kiloamps, current, and the impedance. Now I'm going to use this information that I derived from the MCC when we had the total system put together. And this allows me to, if you will, simulate this particular set of loading. And so I have a 480 volt bus. We have 18,523 and an X over R of, let me see if I can find it, 3.48. And for now, I'm just going to use the same numbers for my single line. What this allows me to do now is do a short circuit simulation for this particular bus. Okay, so I gotta make some current values here for my cables. Now let's go back to short circuit focus, fault the buses. All right, these will be the same branch currents that we'll see inside the MCC. And as we look at our incident energy, well, we don't have any. So this is where I need to put in the individual breaker characteristics that we used in the MCC. So without beating this into the ground, I think you have the idea. And let's say we were using MCC multi-case circuit breakers for these feeders inside the MCC. And for now, let's just go with 150 amp. Just for something to start with. Now I know at the time I said that the breakers for the lumped loads weren't that critical, and they're not in terms of what these calculations are, but it gives us the ability to go through and make some characterizations of what is going to be downstream, and we see that this is fairly benign in terms of arc flash. So this gives me the ability to put at least a label with accurate or somewhat accurate information on here to make sure that operators know when they open up these safety switches that they have the potential arc flash PPE required. Okay, I think that's the majority of what I had to cover. Let's see if we learned anything in this whole thing. So in summary, when we're setting time-controlled protective devices for anything that's arc flash sensing, including differential relays, including the quench device, that it's important to set up the time constraints on the protected bus in the data dialog for that bus, the arc flash tab. And then for motor control center loads, which need coordination, in the type of load, you select whichever motor or load or VFD that has a TCC in the schedule, and that allows us to set up both the load and the motor with the data bus button, and then the protective device with the data button. I think that's what I got. I appreciate everyone for attending. There are a host of other pre-recorded tutorials on the website that get into more detail on both MCCs and motor coordination, and invite everyone, if you've got questions, you're more than welcome to contact us via email or call in at tech support. So let's see if we've got any questions we can answer at this point. Yeah, so the question from Matt is that when we were enter the three-phase fault current as the same for the X over R ratio for the single line, it was a conservative estimate, and the answer is yes. Again, what we're trying to do is verify that there's not any thing we're missing in terms of being able to label a disconnect that may be downstream from an MCC and would be a concern if for some reason we didn't label it during the study. Thank you all for attending, and we'll be talking to you next week. Have a good one.